All right, so why is GIS so important for emergency response? And I'm sure just from the little maps we've already made, you can start to envision, right, the bigger potential uses for ArcGIS, right? So I'm gonna read you all this quote, right? GIS technology gives public safety personnel the ability to manage and analyze large amounts of location-based information. Data can be stored in a geodatabase and used to visualize spatial relationships and reveal trends critical to public safety response and planning. Computer-generated maps can be shared across a network or the internet with multiple agencies to coordinate efforts and maximize resources. Right, so as this image on the right shows that you can have all kinds of data layered in, right, and data from multiple institutions, multiple different branches of government that can share information about, stream flow, roads, population, where buildings are, where jurisdictions are, where hospitals are, right? And then you can start to pile that in, and then you can actually do some calculations to find out, right, given certain road closures, what hospitals are going to be the best to evacuate, so many people in this county too, or whatever, right? So there's all sorts of ways that you can then, do really important work to calculate what's the best way to respond to some kind of incident, and also to plan, right? So maybe, right as we're doing the census right now, so hopefully y'all have gotten your census information in the mail, that, knowing how many people live in a city or a county or a state can then help you figure out what kind of resources you need, where to spend, federal dollars on providing infrastructure, where to put in hospitals, where to put in, fire stations. And so, having that kind of information as populations grow and shrink in areas, to help, realize how many schools need to be built. And so it helps for planning, for, infrastructure, but also, for emergencies, for public health, and stuff like that, right? But you can then, share data across networks, right? So we can go and grab all sorts of public data from our government institutions. Government institutions can share data with each other, and then, right, we can generate different types of maps from all this information. Right, so why is GIS important for emergency response? And so this is a quote from one of the people working at Esri, right, who makes our ArcMap software. Bill Davenhall is the Health Industry Solutions Manager, right? So the company that's making the software has these types of uses in mind, right? They make sure that their software has the tools needed for people that are responding to emergencies, right? So he says, preparing communities to respond to bioterrorist threats or events is a top priority in our country right now. With GIS as a core component to this solution, the immediate impact will be to make GIS an integral component of the day-to-day operations of public health and public safety organizations, right? And so our software is specifically designed to have some of the uses that we're gonna look at here in a moment. Right, so what can GIS do? We already have, tested and experimented with some of this by pulling in spatial data, right, such as state or county jurisdictions and boundaries, and non-spatial data, different statistical information that then you can combine with that spatial data, right, to then create dot density maps or choropleth map, right? And so we can easily draw maps to visualize information that makes it, we can do so much when we can start to visualize this data, to edit and alter existing data, right? So you can go find data that you need from a specific government institution, but then you can alter it and change it to fit whatever purpose that is in the map you're trying to create. We can map distances and areas, right? So, California's dealt with fires over the past few years. And so being able to pull in satellite imagery of the fire Then you can start to trace the outline, calculate the area that it's covering. You can start to predict, right, which way it's heading, which communities are going to be impacted, where evacuations need to occur, and where to evacuate those people to, right? You can grab all sorts of maps from different regions to start to assess this. And then you can create, data that's public access so that people can respond to emergencies with making that data available. Right, so there's all sorts of different scenarios that we can imagine that GIS would be useful for. A hazardous accident or spill, and that's the kind of emergency scenario that you'll be dealing with in the lab over the next coming weeks, right? So marking on the map where the spill occurred, looking up what kind of spill it was, that'll give you information about, right, what kind of toxin it is, how far of a buffer zone you need to create to keep people away, what roads need to be closed, what kind of detours can occur, giving the roads that are available, what the closest public buildings are that people can be evacuated, which houses need to be evacuated, and where those people can go, right? So that's the kind of, we'll be using special tools that help you block roads off, help you find detours and stuff like that, create a buffer zone on a map. Right, but you can imagine all sorts of other things, that like a terrorist attack, a natural disaster, and we've already looked at maps of hurricane tracks. So you can imagine using that to then predict populations that need to be evacuated. And it's not just where the hurricane's going to be, but where the hurricane's not going to be, so you know where people can move to be safe, where they can evacuate to. Right, and then of course epidemiology, the study of disease, and public health. And so we'll touch on that as well, because we're seeing so many important maps coming out of people tracking and trying to communicate about the coronavirus, and really ring the alarm bells about how to slow down its spread, right? And so medical geography is a specific subset of geography and medicine combined, where you can either have doctors using important spatial data to help predict public health issues, or you might have geographers that are doing research to help doctors in the future plan for disease, right? So understanding, how disease spreads through populations, how to model that to prepare for, future outbreaks, or how to see how it's happening, right, in real time to stop the spread of something that's happening right now, as we're seeing. Right, that using maps can help us understand how a disease functions, how it works in human populations. We can discover new information about how a disease works by mapping out how it spreads, right? So the geography can provide research and can provide intelligence. And so these maps here on the right are related to the study that Jon Snow did back in 1854, right? It's not the Jon Snow from Game of Thrones, an earlier Jon Snow who was a doctor in London who was studying, they'd have periodic cholera outbreaks in the city. And it was before people understood what germs were, right? They didn't have the science to see them. And, viruses and bacteria and germs are too small to see with the human eye, and people didn't believe that there was, invisible things coming to get them. And so it was really hard for Jon Snow to convince people that this outbreak was related to germs. And specifically, he was able to use, right, this is before computers, clearly 1854, that he was using very rudimentary geography techniques with drawing out maps, mapping all the different cases of the deaths from cholera and the sickness from cholera, using string and a pencil to kind of map out the different quadrants to, find out how this disease was moving through the population. And he was able to trace it to the water, that cholera travels in contaminated water, which is what we've seen after natural disasters, when, water has been infiltrated by, sewage, that things get mixed up when there's damage to the infrastructure. So there was huge cholera outbreaks in Haiti after the big earthquake. Right, but this was early days for epidemiology, and so Jon Snow was able to map these cases and see that there was a pattern, and that there was, you know, something going on with the water pump, and then had to convince, right, the rest of the medical community that there was these invisible germs in the water. We're going to talk explicitly about John Snow's discovery through early mapping of disease, you know, in a few lectures later on, right? So we can see, you know, that we've known for a long time that spatial analysis can help to solve medical problems, can help us to learn about how disease works. So the main kind of categories for how GIS can be useful for public health are research tools and planning, right? Constructing mathematical models, how disease behaves and how people behave. I posted a story from the New York Times, you know, right next to this where I'm posting this, about how they're modeling coronavirus right now, and how they're using that to help predict how quickly it will spread. Also, you know, how to optimize ways to respond, right? How to provide the services needed, and make sure that we have the resources we needed, such as hospital beds and respirators, right? And make predictions, which is a really important part of how do we respond. We need to predict what's going to happen over the next day, week, month, in order to respond correctly. Then spatial decision support systems, right? So information about what services are available, like infrastructure, right? Are there roads available to get to emergencies? Where are the towns and how many people are in them, and what are the demographics, right? Especially as we're thinking of census, and we're thinking about how coronavirus specifically impacts people of a certain age range, right? Or people that are immunocompromised. And the census at least will give us information about age, right? Which will give us information about vulnerable populations, and especially if they are prone to live in specific areas, whether that's people that go retire to Arizona or in you know, elder care facilities, right? And then what medical resources are available, what hospitals are still in service, how many hospital beds are available, how many are full, you know, clinics that are available. And then, whoops, sorry, gosh. And then emergency response systems, right? So how many 911 operators are available? How many firefighters are available? You know, and then how do we actually collect disease data, right? So that when something is a public health risk, they will actually take your statistics after you've been tested and confirmed and put that into a public database, right? And so we're able to see the current maps of coronaviruses through the collection of, you know, disease register systems and making that publicly available, right? So that we can see where is being impacted and make spatial decisions based on where we see hotspots, right? So kind of the broad overview of applications for GIS in the study of disease, right? Which is epidemiology, data visualization and exploration, which we can actually learn more about the data through, you know, visualizing it, looking for clusters, hotspots, patterns. Data integration, the ability to pull data from multiple institutions and weave it together in a GIS system. Monitoring, right? So as things change on the ground, continually collecting data to see how it changes. Geostatistics and modeling, so using mathematical factors to look at exponential growth or however the disease is behaving, to also look at, right, what kind of landscapes, right? So not all diseases flourish in all landscapes, that we can look at different information about landscapes where the disease can move or not move. Spatial interaction and diffusion, and that's often a function of how people travel, how people interact, where people go, if they go from their home to the school, how many people they interact with at school, and they go to the grocery, then maybe they get on a plane, right? And so looking at how it diffuses through, you know, human behaviors and other impacts that model that. And then data sharing and web services. Being able to share this information is then what allows it to have public policy decisions made based on that data. right? So an example of data integration, we've already been doing lots of this, of layering data on top of a map. We've got some kind of thematic structure and map overlays of data, which, you know, if you pull in two different data sets, you can actually create new information, right? You can start to do some sorts of analysis of risk, to model different problems. You can use some of the tools in GIS to create buffer zones, right, of isolating hotspots to, you know, prevent that disease spread. Right, we see this image on the map of looking at, you know, a landscape where then on top of that is infrastructure such as streets, such as buildings, both public and private, and then, you know, people or customers or whatever, right? So you might be able to look at infrastructure, for example, right, the ability to predict likelihood of elevated blood levels based on the location of a residence, right? That we, if there's infrastructure that's perhaps aging, such as water pipes, and that you know where that infrastructure is and how that might impact certain people that are accessing that water, you could potentially predict that people living closer to certain types of infrastructure that are leaking would have higher levels of blood, lead in their blood, right? So you can use all sorts of, like, you know, proximity to contaminants based on combining different layers to make different predictions and plan for that risk. Right, so monitoring is really part of the aspects that we're seeing right now, is surveilling the disease to be able to see, you know, how it's changing from day to day or hour to hour. And so we can get kind of a snapshot of that disease and then combine how it's changing over time and look at the geographic distribution, look for patterns, clustering, and hotspots, right, which can help us you know, determine the disease behavior and plan for isolation. Right, and GIS gives the ability to manage that large amount of data and then visualize it, right? And then it's being disseminated right now, right? We looked at the Johns Hopkins dashboard, right, which is using the World Wide Web to share that information around the world. It's also pulling data in through the World Wide Web, right, from the WHO, CDC, and several other disease monitoring institutions. It's collecting their data from the internet, pulling it into this mapping system, and then also sharing it back out through the internet. Right, something that's important to keep in mind is that in order to be able to continue to monitor, there needs to be certain infrastructure like data reporting, like functioning internet, right? So there's, you know, parts on the Johns Hopkins map, right, like North Korea, where there is no data, right, which makes it look like there's no diseases. When in fact, right, there's no reporting, there's no sharing of information. So it's not an accurate snapshot, except for what it's showing is that there is no data. It doesn't mean that there's no cases, right? So that infrastructure of data sharing, the ability to access the internet, are important components of the ability to use a GIS well and to have it function for monitoring and modeling. All right, so we're going to look at a couple of examples now, and one of them is going to be valley fever. I don't know if any of y'all have heard of it. It does occur in California. You can see in this image the red spot where it's highly endemic, which means it is established there as a disease, and that it tends to spread around to human populations there. The other place where it's highly endemic is in Arizona around Tucson and Phoenix in that desert there. There's then, you know, kind of that peachy mustard color where it also exists, although we may not see outbreaks as often. And right, that's the entire Central Valley of California, the entire, you know, desert regions of Southern California, Southern Arizona, Southern New Mexico, and West Texas. There's also then kind of the dotted red line showing us that it's suspected to also be occurring quite a bit in northern Mexico, but for some reason either there's not a lot of populations that are interacting with it, or there's not a lot of testing and data reporting from the population there. Right, so valley fever is a fatal dust-borne infection that's caused by fungus that lives in the soil, right? So there's tiny spores in the soil that can get picked up by wind and then inhaled, and then it gets settled into your lungs and can cause all kinds of pneumonia-like symptoms, right, such as coughing, chest pain, shortness of breath, headaches, fatigue, and fever, right? So actually these are all very similar symptoms to coronavirus, right? When you get something that's lodged in your lungs and doing something there, it's never good. I call this valley fever lung fungus, which probably isn't super accurate, but sounds like you've got mushrooms in your lungs and it's pretty gross, right? That we've had upticks in these cases, since, the past couple decades, right? You can see in this graph that since 2009, there's the rate per 100,000 people has jumped way up to 51 per 100,000 people, right? So California's seen a large increase. There's been quite a few in Arizona. And people think that probably the reason we're seeing more of this is a combination of environmental factors that, that we tend to see more when there's a drought. When there's a drought, right, the soil is dry, which means that when the wind blows, it's easier for it to pick up small particles and then for that to make its way into the lungs. Not just the people, but actually dogs are prone to get this because they also dig in the soil. And when they dig and they stick their noses in holes and stuff, they breathe it right into their nose. And so dogs and humans both are susceptible to this. And so they think drought has been a factor, but also development. So when you see the disturbance of soil, so soil can get packed down and kind of thrown over, but when you bring in machinery that digs it up, that loosens that soil, that plus drought can make it easier for it to get caught in a breeze and inhaled, right? Doesn't sound any fun. Right, here's just what the biology of the fungus looks like, where in image 1, it's these, long chains of spores growing in the soil. When the breeze comes, they start to snap off into little particles. Then you breathe in the air, breathe it into your lungs, and then it starts to grow in there. It gets deep in your lungs and starts to create more spores and, I don't know, mushrooms maybe, and grow into your lungs, which makes it really challenging to continue. Some people recover after a while without too much issue. And then of course, right, it's people that have other lung issues, other immune issues, or people that are prone to disease or more elderly that, right, can die from this. Right, so I knew a graduate student at University of Arizona that was using GIS to analyze, where they saw outbreaks of valley fever, what the conditions were, and then to look at the conditions and predict where we expect to see more outbreaks, right? So pulling in multiple data sets, right? First of all, just knowing where valley fever exists, so where it's endemic, where it's occurred before. Then looking at different climatic factors, right? So, they tend to see that when there's a rainy year, it helps the fungus grow in the ground. And then if the next year there's drought, then you have a lot of spores in the ground then the soil is drying and that's getting picked up in the dust, right? So multiple years of climatic issues that influence where you might see an outbreak. Then where you've seen some kind of disturbance, right? So housing development, or if there's been some kind of fire that, kills the roots which keep the soil on the ground. Other landscape factors, that if there's lake beds that have dried up and left sediment, available to blow in the wind, dry fields or farm fields that have been, left dry for a year, maybe they're not going to grow something there. They're just letting the soil rest. Then when it dries out, that soil can take to the wind, right? So you can pull in information about disease, about climate, about land use, to start to figure out where we expect to see occurrences of valley fever. And of course, all these things have to be happening near a population, right? Because if there's not people there getting sick, nobody cares, right? So we see here on the left, there is a map of land use, right? Where there's urban areas, we know people live. They're then using, different reflectances of the soil to know where there's fields that are dry, where there's fields that are wet, where there's fields that are open soil, right? To start to, imagine where they could see soil getting picked up in the wind fairly easily. You can layer that on top of the map up here on the upper right, which is places where we know that the disease lives, right? You don't want to look for it in Utah because it doesn't, that's not a place where you'd expect to find it at all. And then, right, there's information from the US Drought Monitor, so you can start to look at, months and years of climate data, looking at rainy years and drought years to help you expect, this is going to be a drought year after a rainy year. So we know in, this suburb of Phoenix, we might expect to see an uptick in valley fever cases, right? And so it can be used to predict where you expect to see the disease. You can also look at where disease happened and start to look at environmental factors to help you support your next model.